Hey folks, good morning, and apologies for the slight delay in getting started. There were some issues with the stream and YouTube logging me out for absolutely no reason, although it didn't tell me that I was being logged out, so whoops. The joys of living in 2020 is that, an entire lecture can be derailed by YouTube logging me out of my account. All right, so with that said, today we are covering our very last lecture of Unit 2. Friday is the Unit 2 exam. A couple of reminders about that. One additional problem. Hopefully each problem will be a little shorter to compensate. Roughly the same level of difficulty. And finally, the hopefully no cheating, because last time that was a problem. And the really bad notices have been sent out, and I'll be sending out the rest today. So the other thing I want to mention is, per request from Dr. Mueller, we are actually not going to be opening the exam at midnight. So for those of you who had intended to stay up late and then just start it and get it out of the way at the beginning of the day, I'm afraid you're not going to be able to do that. The bad behavior that happened during exam 1 just has left us nervous about the extra time that leaves open for abuse, because if somebody does something with ill intention, like at midnight, let's say, then it has plenty of time to propagate forward so other people can abuse it later on in the day. Starting later is not going to completely erase this concern, but it will, if nothing else, make the window a little bit smaller. So the exam's going to be open from 8 a.m. on Friday, and then that will stay open, obviously, till the end of the day. So for the small handful of you who I know took advantage of the, let's say, really early morning time slot, I apologize. This is just, unfortunately, a reaction to bad behavior on parts of your peers, and it is why, unfortunately, we can't have nice things. Other than that, though, no major changes, just the ones I just listed, and we'll see how it goes. And if it's good, great. If it's not good, we'll continue to adjust, and we will go from there. Okay, so with that said, today we are covering our last topic of Unit 2. And it is worth noting that this upcoming exam is only on Unit 2. I know we did cover a single lecture from Unit 1 after the exam. That will not be on this exam. It's just the stuff in the Unit 2 section on Brightspace. Any material that we cover in a unit after the exam, just imagine that that's going on to the final associated with it. So that whatever it was, lecture 11, I think, which was the very last lecture in Unit 1, that will be in the Unit 1 section of the final, not Unit 2. Okay. So today we are covering our last topic, which is RC circuits. This begins a series of circuit types that we'll cover kind of scattered throughout the rest of this course, where we refer to them by a combination of letters. Here, R and C, to indicate that it is a circuit with a R and C. Yes, there's a question in the chat, will the exam still be available, will the evening still be available for the exam? Yes, absolutely. Like I said, it'll open at 8 and it'll be open all the way through the rest of the day until 11:59 p.m. So it's just the early morning that's being affected. So no worries there. In this particular thing, we are talking about an RC circuit, which means it is a circuit that has an R, a resistor, and a C in it, a capacitor. So now we are looking at hybrid circuits that contain both of the circuit devices we've been analyzing thus far. And we're going to see that leads to some interesting and time-dependent behavior. Now, most of the circuits we're going to deal with in this in this lecture are related to this very simple fundamental circuit that I'm showing you here, which is a resistor and a capacitor connected in series with a switch that can either be connected to a battery or connected to a wire. Now, this is relevant to a discussion that we've had in the past, albeit briefly, about how switches affect circuits. And the way I really suggest you consider these is you draw a version of the switch when the switch is in one position. So for example, when the switch is in position A, and another version of the circuit when the switch is in position B. And we kind of analyze each of these separately, so we can see the sort of very disparate behavior between the two arrangements for the switch. Now to that end, I'm just going to do a little bit of, oop, that was too large. A little bit of bookkeeping here. I'm just going to give myself room to draw my resistors and capacitors. So in both cases, we're going to have the resistor connected to the capacitor. That's going to be the same for both orientations of the switch. Now the big fundamental difference is that when the switch is in position A, these devices are connected to the battery. So we're going to see that there's a battery in this case over here. By contrast, if I look at when the switch is in position B, that is to say down here, note that the branch of the circuit that contains the battery no longer is connected here. So that is like the case from our quiz last class, is going to have no current flowing through here, so it's like the battery doesn't even exist when the switch is in position B. So that's why I've drawn this circuit here. Now, for each of these, I'm still going to have my two circuit components. But I think it's probably obvious just from looking at these two circuits that my circuits are going to be doing two separate things. Now, in short, when I have my switch in position A and my capacitor is connected to my battery, the battery is going to start driving current through the circuit. Now that current represents moving charge, so let's just imagine I have some charge moving along the circuit in the direction of the current here, and it's going to get to the capacitor and something's going to happen. Notably, as it's flowing through, it's going to get to the capacitor plate, and then it's not going to be able to go any further, right? Because remember, capacitors are separated by an insulator. Current can't flow across the plates. So instead, what's going to happen is the current that the battery is starting to push out is going to start piling up on each one of the plates. One of them is going to collect positive charge, and one of them is going to collect negative charge. Really, what's going to happen is the electrons in the circuit are going to be pulled away from this plate and pushed onto the other plate, leaving you the positive and negative here. This is, again, as the result of current coming out of the battery. Now, because of this, because charge is being added to the capacitor, we call this arrangement a situation where the capacitor is charging or charging up. By contrast, if I let this happen, eventually the capacitor will become full. If the capacitor becomes full, and then I switch the switch to B, now the battery isn't going to be there anymore. Note, this means there's going to be a ton of charge on my capacitor and no battery to hold it there. Well, this charge that's all, stuck on this capacitor does not want to stay there. In no way, shape, or form does it want to remain where it is. So this capacitor is actually going to shed all of that excess charge in the form of pushing a current back through the circuit in the other direction. Now, because the amount of charge in the capacitor is decreasing, we say that it is discharging. And the next couple of slides are going to analyze very closely the behavior of each one of these phases of the capacitor's operation. Now, yeah, good. So a couple of things that we're going to need in order to do that are the Q, that's the amount of charge on the capacitor. I, that's the amount of current through the resistor. So there's a question in the chat. Can I explain again why there's no battery on switch B, but there is on switch A? I mean, just look at the circuit over here. If I imagine I have the switch in position A, that's my circuit, clearly containing the battery. But if I have my switch in position B, this is my circuit, does not contain the battery. And in fact, in this particular situation, the branch that does contain the battery isn't connected to anything, so no current will flow through it, just like we saw on the lecture quiz from last class. Hope that clarifies, clears up your question. Where was I? Right. The current through the resistor, which, by the way, for the purposes of our convention, we are assuming is to the right. We'll see that that's actually not the case. But this is important for determining polarities of our circuit. So those are the two circuits we're going to sort of analyze here. Now, the current through that resistor is going to be related to the rate of change of charge on the capacitor. So this is the derivative of this. We can then find the voltage across the resistor using Ohm's law and the voltage across the capacitor by using the definition of capacitance. And all four of these are going to get used in each of the next slides as we try to derive a mathematical expression for the charge on the capacitor and the current through the resistor. Now, to do so, I'm going to go ahead and steal my little circuit diagram here. And we're going to go to the case where the capacitor is charging. So that's this scenario here. This is when the switch is in position A. Now, in order to analyze this, what we're going to do is apply a loop rule, like Kirchhoff's laws, just like we normally would. So you'll note that I've already labeled my current, I've already labeled my polarities, so all I have to do is do my one loop analysis. Now, my loop is going to have my battery, and then that's going to be a gain because I'm coming up around here, so that's negative to positive. Then I'm going to lose the voltage across the resistor, which is I times R. And then I'm going to go from positive to negative, so I'm going to lose the voltage across the capacitor. That's minus Q divided by C. And then I am back to my initial point, and so that loop is going to add up to 0. Note, that's just what I have written right up here. Now, at this point, we actually have to do something very different to solve for this. Now, the reason it's so different is because my current, I, actually depends on my charge, Q. Specifically, my current, I, is the derivative of charge with respect to time. So this here, well, aka this, note that this is just, I'm just writing out what's already on the slide because I know this can sometimes be a little bit too dense. So I'm just doing this off to the side. And in fact, maybe what I'll do, just for clarity, is fail to draw a rectangle. There we go. We'll just get rid of that for the time being, just so it's not distracting us, and we'll just focus on what's going on over here. Now, what we do over here is we've plugged in I for the derivative of charge with respect to time. Now, this is where things get a little bit tricky, because this is not an equation that can be solved algebraically. In fact, this equation can only be solved using calculus. This is a differential equation, and we will need to solve it as such. Now, our goal here is going to be to isolate the derivative in this formula. This is we're applying a one second. a very straightforward method of solving simple differential equations like this one called separation of variables. And the steps that we're going to follow are straightforward. We're going to first isolate the derivative. Which means we're going to use algebra to get the derivative all by itself. We can do that simply by moving the derivative over to the other side. So plus e minus qc equals dq dt times r. Then we're going to divide both sides by r. Now, before we do that, what we're going to do here on the left-hand side, just for convenience, is we're actually going to combine these two fractions. So I can multiply this first term by c over c. These two fractions then have a common denominator such that I can write them like so. Then I can divide both sides by r, and I get this expression here. And so this is just isolating the derivative, and you'll note that that's what's written right here. Now we are actually going to go through the process of separating the variables. What do I mean by that? Well, I want to get everything that depends on q on one side, and anything that depends on t on the other. Now, this is actually relatively easy to do in the first step. If I just multiply both, if I pretend my derivative is a fraction, and I multiply both sides by dt, well then it would cancel out over here, and I would end up with dt on the left. Now, this is one of those things where a mathematician and a physicist, and perhaps even an engineer, might disagree on exactly what's happening as far as whether or not it's okay to just pretend my derivative is a fraction. Suffice to say, I'm a physicist, and at this level, it's fine to believe it that way. It is worth noting that in actuality, there is a sort of deeper calculus concept that allows us to treat it this way. But for our purposes, this works, so we're going to do it. Now, this gets rid of the problem of isolating q and t. Now my differentials are going to be on other sides of the equation. But note that this term here still has a q in it. So I'm going to take this term in parentheses, and I'm just going to divide both sides by it. Leaving me an expression that looks like this. Now, I have succeeded in separating the variables. Note that r, c, and e, those are all constants, so it really doesn't matter what side of the equation it's on. So I'm happy with this separation of variables. The next step is to then integrate our result to get our final answer. And that's what's hidden behind my little box up here. I integrate both sides of this equation. Note my dt over rc is integrated with respect to time, and this side of the equation is integrated with respect to charge. I just go from t equals 0 to some time later, and I go from 0 to whatever the charge is at that time t. Now, the right-hand side of this equation, well, that's really, really easy to evaluate, right? It's just dt. Rc come out of the integral, and so the integral of dt is just t. So I just get t over rc on the right. On this side, though, it's a little bit harder. My q is in the denominator. So I would have to do a u substitution, and if I did so, I would see that I'd get a logarithm involved, a negative logarithm. And so I get this expression right here where I've done that u substitution and done my integration out. At this point right here, I'm not quite done. Our goal is to get q as a function of time, so I want to solve this equation for q, which means because I have a natural log over here, I need to take the exponent of both sides. So on the right-hand side, I get e to the negative t divided by rc. Note that my negative sign, I move it over here, and then I take the exponent, resulting in this. And when I take the exponent of a logarithm, I just get whatever is inside the logarithm. So that's right there. Once I have that, I am basically done. And I can solve that for q, and I get this expression right here. A couple things to note about the behavior of this equation. One, if I plug in t equals 0, and maybe I can actually write this down over here. I get 1 minus e to the 0. E to the 0 is 1, so I get 1 minus 1. So this whole thing becomes 0, which says that the charge on my capacitor starts off at 0. This makes sense. We are in the process of charging the capacitor up. It should start at 0. So it starts at 0, and it gradually increases over time. If I take the limit as t goes to infinity, I get q equals ec 1 minus e to the negative infinity. Well, e to the negative infinity is the same as the reciprocal of e to the infinity. And if I take 1 and I divide it by an infinitely large number, that gives me 0. So this will just give me 1, which means my final value for q is just e times c. And you'll see this line asymptotes to that value. Once I have this equation and I understand its behavior, makes sense, starts off at 0 and it ends up at the maximum amount of charge that that capacitor can hold, I can then just take the derivative of this equation to get the amount of current in the resistor. And that gives me this second equation down here. Note that this is a little bit simpler. This is just a simple exponential decay, which tells us that the current starts at its maximum value, given by Ohm's law, voltage divided by resistance, and it quickly decays to 0 as the capacitor fills up. I would like to keep this stuff here. Unfortunately, I think I am out of room. No, I'll make that note at the end. So interestingly, we can do a couple of things here to write out some rules of thumb for our charging scenario. If rules of thumb. At t equals 0, current is max. Then the capacitor behaves like a wire. What I mean by that is at t equals 0, the capacitor allows current to flow freely. So you could, for example, redraw this circuit with just a wire in place of the capacitor, and that would give you, at t equals 0, the actual value of the current in this circuit. Similarly, a long time later, the current through the capacitor is 0, at which point the capacitor is going to act like a brake in the circuit. It won't let any more current through. And we'll see those rules of thumb come into play later when we work on some practice problems. But for now, this mess of a slide was to get us to these two results, which we then kind of talked about. And remember, what we did was we started off with, and I'll call this step 0, a loop rule. Then we solved the resulting equation by separation of variables, which involved isolating the derivative, separating the variables, and integrating the results. I say this in these, illustrate these steps clearly because we're going to have to do the same thing for the discharging capacitor. However, we are not going to actually go through that process. I'll give you the loop that we're going to analyze. We're just going to go around and we'll do, say, the resistor and then the capacitor. Note that when we do that, we gain IR, and then we gain Q divided by C. And then we're going to solve this equation using separation of variables the same way we just did. Write down our equation, isolate the derivative, separate variables, do the integral, get the result, solve it algebraically, and we get these two results here for the charge and current. Now we note that the charge is an exponential decay, and the current is also an exponential decay. But I actually want to mention that this graph down here is a little bit misleading. Note that this is negative I. This graph would actually be better represented if this is time and this is current as a exponential decay in this way. It starts off at a large negative number and then decreases to 0 with time. Note that this is consistent with our expectation that the current is going to be pushed in the opposite direction. Okay. You can check the notes if this is unclear, if you're looking for more detail. Let's see. There is a point that I want to make here, but first I want to just talk about a couple of things real quick. When we're talking about the process of charging or discharging, what's really happening is energy is being moved around the circuit. When the capacitor is charging, the battery is providing power at a rate of voltage times current, i.e., some of that power is being dissipated by the resistor, I squared R, and some of it is being stored in the capacitor. You can calculate the power that is stored in the capacitor by multiplying the current through the capacitor times the voltage of the capacitor, which gives you IQ over C. Note that even though the charge itself is not actually passing through the capacitor, it's stuck on the plates, the circuit still behaves as if current is flowing through. So there's no trick here. Like all of these currents are not 0. Like none of these currents are 0. Nothing weird is happening until you've waited a long time and the capacitor is fully charged up. Now, we can basically take our loop rule, which gives us voltages, and multiply it by a current to give us the way energy transfer goes. So the battery provides the power, and the capacitor stores it, and the resistor uses it. Similarly, when a capacitor is discharging, the same thing is true, except now the battery isn't in the circuit anymore. Now I becomes negative, and note that I have an interplay here. Instead of both of these using the power, what we're going to do is move the capacitor over to the other side, and we're going to see that the capacitor is now providing power, which is being used by the resistor. You might wonder why on earth we would ever have a situation like this. And I can show you this. This is a camera flash. This is a great example of a circuit that depends on a capacitor. And I'm going to see if you can actually hear what's going on here. Now, I'm going to turn this on and hold it up to my microphone. Hopefully you can hear something, and if not, we'll see. But hopefully what you're going to hear is a high-pitched whine. That high-pitched whine is the batteries, just regular plain old AA batteries, providing current to charge up the capacitor. So hopefully you could hear that a little bit of a high-pitched whine. Now eventually, if I look here on the back of my camera, a red light's going to shine up, and you'll note that this is taking a long time. But now that that light is on, it's telling me that my device is fully charged. And of course, this means I have had my circuit in position A for a sufficiently long time that the capacitor is fully charged. Now, I'm going to switch into position B, and well, I imagine you can guess what is going to happen. Well, you can't really see it because, well, maybe if I pointed at myself. Yeah, you see the little bit of a white flash every time I do that. That white flash is the capacitor discharging it very rapidly. Discharging very rapidly. You'll notice right off the bat that the time scales of these two things were very different. It took a long time to charge the capacitor up, and it flashed very, very rapidly. Now, that is actually as a result of very complicated electronics going on in here. It turns out this process should actually be symmetric for a very simple circuit like this. The battery should charge up the capacitor in the same amount of time it takes to discharge. Now, in a device like this one, what's actually happening is you're using sophisticated electronics to charge up the capacitor more than you would normally be able to. You get a real big capacitor in here, and you have to charge it up very slowly. So basically, there's a separate charging circuit that uses the voltage and uses resistors to make it take a really long time, and then that switches to a different discharging circuit. Doing so allows you to get brighter, faster flashes than you would normally be able to with the batteries. And this right here encapsulates the difference between a capacitor and a regular battery. Both of them provide current to circuits, but a battery does so slow and steady, whereas a capacitor does it very quickly. And that's the sort of fundamental difference there. Now, we can quantify how long this process takes. In addition to other useful physical properties of a circuit, we can define a value, resistance times the capacitance, RC, as this variable tau. This is the time constant of the device, of the circuit. It tells you how long it takes to get the capacitor charged up 63% of the way, or alternatively, discharged 63%. Note that this number is not chosen arbitrarily. It's the value you get when you plug -1 into the exponent and then you subtract 1 from it. So it's the value of this equation when T divided by RC is equal to 1. Now, you might be surprised to learn that when you multiply a resistance by a capacitance, you get units of time, but you do. If you actually go into the SI units, you in fact do get time. We can see that, in fact. Resistance is ohms, sure, but another way of thinking about that is, actually, do I have time for this? Unfortunately, I don't have time for this exercise. I'd love to spend an extra couple of minutes, but now that I look at the clock, we only have 13 minutes left, and I want to make sure I definitely get through at least one, if not two, practice problems. Suffice to say, it's a fun little exercise. See if you can convince yourself that the units of the time constant are, in fact, seconds. One other thing I'd like to make, when we're talking about circuits, we often say the phrase "a long time later" as a way of suggesting that we're waiting for the limit of t goes to infinity. But of course, it's not actually practical to wait until infinity, right? So the question becomes, what satisfies long enough to let this kind of settle into its final state? And a good rule of thumb is that when you've waited an amount of time greater than or equal to, say, roughly 5 times the time constant, you're probably in good shape. This is not a hard and fast rule, but it is a reasonable enough duration to wait to constitute a sort of a long time later. Okay, that's all the learning we have as far as new stuff goes. So let's do a couple of practice problems. I'll note that we've got practice problems. That's 1, 2, 3, 4, 5, and then we have the quiz. So we are definitely not going to be able to get through all of these. I think what we will do is we will do one that is simple, and then we will do one that is less simple to kind of give you an idea of how this circuit behaves. Now, in this circuit here, we have a situation where my capacitor is discharged, so there's no charge on it, and I'm going to close that switch that I've labeled S. So the first step for any problem is to identify if the circuit is charging or if it is discharging. In this particular case, we say that the capacitor is started off discharged, and I am closing a switch. Note that when I close that switch, it's going to connect my capacitor to a battery, and as a result, this is definitely a situation where the capacitor is charging. Now, it might be worthwhile to come back and actually write down our equations for the charging scenario here, but we're actually going to instead use our rules of thumb to try to get an idea of how these should behave. Now, so just kind of using our rules of thumb, which is to say cap allows current to flow freely at t equals 0, so it kind of acts like a wire. And it acts like a break in the circuit as t goes to infinity. I'm just going to sketch the circuit and see if we can infer and make an argument for what these things might be. Now, what I'm going to do to that end is I'm just going to redraw the circuit in both cases. And let's see, I need to get rid of room for a battery, a resistor, a capacitor, a resistor, oops. And this is just a way of sketching and kind of developing an intuitive idea of what you expect to be happening in a circuit. So we've got our 2 ohms, 2 ohms, 2 ohms. And the idea here is that we are just going, for the sake of our hypothetical situation, we're going to say this is at t equals 0. The capacitor can allow things to flow freely. So we're going to replace the capacitor with a wire. We're going to pretend, just for the beginning, that the capacitor is a wire, and we're going to analyze that circuit. Well, if I just look at this, if current is allowed to flow freely through the capacitor, then it's going to form a short circuit. It's actually going to allow all of the current to come out of the battery. When it arrives at this junction, normally some of the current will go down, but some of the current will go forward. But this is the source of the age-old adage, current follows the path of least resistance, which means more current goes to branches that have less resistance. And in this case, in fact, this branch has 0 resistance. And in that unique case, all of the current is going to go that way. So what actually happens is this center branch does not contribute, and this is my result. Well, I can very easily calculate what goes on here. I have got 2 resistors. They add up to give me 4. 12 divided by 4 is 3 amps for current 1. And recall that current 2 was the current in that branch that I just labeled green, and that should be 0. Similarly, as t goes to infinity, I'm going to repeat the process, draw my little circuit, do my little rule of thumb. I got a battery, I've got 3 resistors, but now my capacitor is full. It can't accept any more current, can't accept any more charge, so it acts like a break in the wire. So what that means is I now have a break in my circuit. The only thing that actually has current flowing through it is that little bit that I just highlighted. All 3 of these are in series. That's the case because it is as if that exterior branch does not even exist. And so I just do 2, 4, 6. 12 divided by 6 is 2 amps. Now note that the current over here, I1, will now be 0. And the current here, I2, will now be the 2. 12 divided by 6. So as you can see, you can actually analyze certain capacitor circuits without any need for advanced formulae. Now it is worth noting that you can in fact find these results as well using these formulae. What you would do is you'd plug in T equals 0. Well, T equals 0, I know that gives us 0 current, so that would tell us there is 0 current going through the capacitor. So I1, which covers the amount of current going through there, would give you 0. Sorry, that was the charge. Sorry. By contrast, I actually meant to point out this equation. Yeah, the actual current. T equals 0, that gives me 1, so that current is E divided by R. But note that you have to be very careful when you're analyzing these circuits to know when other circuit elements are being ignored. And that's why this sort of rule of thumb becomes helpful, because if you redraw the circuit, you can get an idea of which things might be shorted out, which things have current flowing through them, and so on. Can, of course, log in and double check the notes here to make sure I didn't do anything wrong, but this should be fine. It's also worth noting that your notes will go through this example a little bit differently, which is probably in our best interest. Yep, but 3 amps and 2 amps. Yep, we're all set. So again, I'd like to remind you that all of these practice problems are worked out in full detail in the notes with a full description of them. And I strongly encourage you, you look into how those are evaluated. Now, you'll note that the gross majority of these problems do, in fact, have very simple solutions. Now, let's see, is there one here that is doing a discharge? Most of these are charged. But let's see if we can just look at which one of the, I don't know, maybe this one? Sure. Okay, here we have a circuit with no switch, and we're just told that this circuit has... Okay, so as there was a question in the chat, at T equals 0, why don't I consider the other resistor? Remember, I said this explicitly, that this here represents a short circuit. All of the current coming out of the battery, where it would normally divide, when there is a short circuit, instead, all of the current goes through here. So the only non-zero current in this case is the current going through this branch. You can do this using a loop rule if you really need to convince yourself of that. You can do, label this, call it I3, call this I1, call this I2, do a loop 1, say a junction, and I don't know, maybe do your second loop in there, and you will be able to solve for it, and you will get I2 equals 0. So you can prove this rigorously if you are really unconvinced that a short circuit has the effect of removing this resistor from the sort of calculation. Unfortunately, we do not have time to go through that right now because we only have a couple minutes left, and I would like to do at least one more practice problem. It is a good question, though. I strongly encourage you to go through and actually do that loop rule calculation if you haven't already. Well, sorry, if you haven't already. Of course you haven't. I just said so. But if you are unconvinced, that's what I meant to say. Okay. So this is another case where it is useful to use our little rules of thumb to kind of get a feel for what's going on here. This circuit has been running for a very long time, and what we're meant to assume here is that this capacitor has had plenty of time to charge up. As a result, this is at its maximum charge Q. Now, we want to do this as quickly as possible because I don't have a lot of time yet, so we're going to use our same rule of thumb. At t goes to infinity for the case of a charging capacitor, capacitor acts like a brake. So when I redraw this circuit, I'm going to have a resistor, a capacitor, sorry, a battery, resistor, battery, and I'm pretending like my capacitor is a brake in the circuit. So note, that means no current runs through this branch or this branch because there is a gap. Current can only flow through closed circuits. This means that this is the only portion of the circuit where the current is actually flowing. So just like before, we're going to be able to evaluate that as one single closed loop. And that should not be 12, that should be 18. Apologies. And if I just look at that blue loop, it's the three resistors are in series. 2 plus 2 plus 2 is 6. 18 volts divided by 6 ohms is 3 amps, and that's going to be the answer for the current through the 18-volt battery. Note that I didn't say this explicitly, but this is a situation where the capacitor has been charging for a very long time, just in case it was not clear. Now, the total power dissipated in the resistors is relatively straightforward as well. Power, that is not a P. Power can just be calculated as I squared times R. And each one of those 2 ohms has 3 amps running through it. So it's 2 plus 2 plus 2 times 3 amps squared. But note, there is another resistor down here. And you could write out what that is. It's 2 ohms, but it's times 0 amps squared, so that does not contribute. As a result, my power is just 6 times 9 equals 30, not 36, 54. Mathing is hard. And that's the power through the resistors. Now, ultimately, the question is, what is the charge stored on the capacitor? Now, that is actually something that is a little bit interesting. We would want to use the loop rule here. And I want to emphasize how important and how useful and how versatile the loop rule is. Because the loop rule is going to tell you, when you come back and you try to apply these equations, the loop rule is going to tell you what value for the resistance or the capacitance you are going to want to use. Because I set up my loop rule here, where are we? Here we go. And I go around that secondary loop, I get 4 volts minus 2 times 3 amps minus 2 times 0 amps. Note that this has 3 amps through it, this has 0 amps through it, minus Q over 5 nanofarads. That adds up to 0. And now my loop rule right here becomes 4 minus, what's that, 6 equals Q over 5 nanofarads. And I have made a small sign error, and the reason I've made a sign error is Y. Because this should be positive. Should make that negative, which would give me negative, well, I realize I'm writing behind myself now. Let me get out of the way. Negative 2 volts equals negative Q divided by 5 nanofarads. The negative signs are going to cancel out, and there appears to be a typo in the notes. 2 times 5 is not 20, 2 times 5 is 10. So 10 nanocoulombs. Sorry that this last example was a little bit of a mess. Like I said, these are all worked out in the notes. Work through them. I do want to mention you will have one RC circuit on your exam. It will be the 4th and final question. It will probably be simple and straightforward like the various examples in this lecture notes. Couple of hints about the circuits. This is, the quiz for the day. For each of these questions, you're going to be naming the circuit in which the charge flows into the capacitor at the highest rate. So that's the best maximum current, or the highest maximum current, the initial current rather. Then you're going to name the circuit that has the most charge, and which one gets 63% full in the shortest time. The hint I would like to give you is that these 3 things that are calculated down here, initial rate of current, total charge, and the time constant, these 3 things are going to, these 3 values here on the left are going to be very useful when determining what goes on in each of these. All right, with that, we're done with Unit 2. I got to get to my next class. If you have any questions or comments, you can shoot me an email. I'm basically booked solid with appointments more or less for the rest of the week. I think I have a little bit of availability on Friday. I might open up some office hours on Thursday, but I will need folks to email me if that is something they are interested in, just to prep for the exam. Otherwise, folks, I will make an announcement about the exam today on Brightspace with any last-minute information that you need. Don't forget, you do have practice problems that are available on the Brightspace, and other than that, hopefully it will go nice and smoothly. All right, folks, I will not actually see you on Friday, but I will be watching your exams closely, and let me know if you run into any trouble or have any questions. Good luck studying. I do want to mention briefly, because there was a comment in the chat, and just in case folks watching the restream are not paying attention to the chat, there was a question about whether or not walk-in office hours are changed. No, obviously, well, not obviously, but my walk-in office hours are unaffected. So 11 to 12 today and 11 to 12 on Friday, I will be in my Zoom room available to answer any questions that you might have. Good luck.